Welcome everyone. In the last lecture, we defined stress and we have also defined traction, and we have also correlated them using the Cauchy's definition of stress. And in this lecture, we will again do a neighboring concept towards our broad goal of solving elasticity problems. We have to finalize the governing equation, and towards finalizing the governing equation, we have first defined strains, then stresses, and now we will work with conservation laws and then define constitutive relations, and then combine all these concepts of strain, stress, constitutive relations, and conservation laws. All these 4 or 5 sets of concepts, we're going to combine them to get the governing equations and then solve the problems. So now let us pick up this particular topic on conservation laws. Conservation laws are not unfamiliar concept, are not an unfamiliar concept to you guys. So normally when a conservation law is being told, it is told in terms of velocity of a particle or sum of kinetic energy and potential energy are constant. We will still mean the same things, but instead of idealizing a block as a point, we would work with respect to the elastic nature of an object. Any material, realistically speaking, will undergo some amount of deformation when it is being subjected to a external load. By load, we mean a force or a moment. Or it can also undergo deformation when it is subjected to internal loads as well. Right? So keeping that in mind, we will revisit these conservation laws, which we have been learning for some time. The 4 main conservation laws which we have are conservation of mass, linear momentum, angular momentum, and energy. So we will revisit these in terms of the elastic, by taking in view of the elastic nature of the material. So normally we write it in terms of position vector and velocity vector. We will expand the horizon and we will try to write it in terms of displacements, stresses, and strains. Okay, that is the goal. We will revisit. So basically, we are revisiting an old concept with respect to these new definitions. We will start with conservation of mass. So I have an object or a body B, and I am considering any region or any volume of that region, and I am designating that volume of the region as V. Okay. What is P? P is a point on the volume V. All right. So P is a particular point and V is the corresponding volume. So let me mark P here. P is any point in the volume P and V is any region in the body P. Okay. And conservation of mass is this particular equation, dou rho by dou T plus del dot rho, basically divergence of rho U is 0. Now, how does one get to this equation? You draw a control volume, you pick any region, any square element, not a square, a cuboidal element, dx, dy, dz, and try to identify the amount of mass flux into this region and out of this region. And that is how you end up with this particular equation. Where what is rho? Rho is the density, and u dot, the dot, overhead dot. The overhead dot always for us indicates derivative with respect to time. All right. So conservation of mass, there is not much of a complication. This is very similar. In fact, this is identical to the one which is used in fluid flows as well. Okay. So here in conservation of mass, we do not have these concepts of stresses or strains. All we are saying is there a mass coming in on, is there a mass going out? And in particular, when we in solid mechanics, this particular equation does not does not interfere with the governing equations, mainly because there is no flow in solids. Essentially, what we are saying is the mass does not move around. Okay, there are local deformations, but it does not translate to mass of mass moving from one region to the other region. Second one is conservation of linear momentum. So I will first define these particular terms. So I'm going to use the following terms in the next sets of slides. V refers to the volume of the body. When we say body, we are referring to this any region of a body B. Okay, that is when I say body, it's that local body which is being represented by this. I should have perhaps used a different symbol for this. Perhaps you guys can put it as dou omega and the surface area also as dou omega. Okay, so we have an object, and in that one can choose any region which is designated by omega, and V corresponds to the volume of omega, right? So body force is, what is body force, by the way? Body force is, as you can see, is a force which acts on a body. But does it mean it also includes the external object? No. External forces? No. So if there is an amount of water in a particular beaker and you put a stone on it, there are two kinds of body forces which are acting on it. One is the gravity and second is the buoyancy. These are acting all through the body, all through the volume of the body. They are not just acting at a point or on a surface. They are just acting all through the domain of the object. So forces which act all through the volume of a particular body are referred to as body forces. The common body forces which one encounters is the gravitational force. And if the object is submerged in a fluid, there is also a corresponding buoyancy force. So typically these are the ones. Or if the object has some kind of a charge distribution and there's an electric field, that also can be counted as body force. Okay, unless the object is metallic, then it becomes only a surface force, right? Because charges redistribute. All right, so coming back to linear momentum. So we are considering an object, any object. If I consider a particular region, and if V denotes its volume, and there are body forces in it, and there are also tractions on its surface. And if I try to look at the net equilibrium, which is denoted by F net, the net force on it, I can say it is the sum of the body forces as well as some of the external forces. At present, we are assuming that there are no internal forces. Okay, rather internal tractions. Internal tractions get nullified with one another. Okay, so in case of static equilibrium, all we say is, okay, whatever forces are acting through the domain and on the periphery of the domain, which is called as a boundary, we are saying this is equal to 0 because there is no net momentum in case of static equilibrium. Likewise, one can extend this towards saying, okay, this is equal to the rate of change of momentum of all points. Okay, I'm integrating it over the volume because I'm integrating at every point. I'm accounting for at all points. So this is the dynamic equilibrium equation when it comes to linear momentum. So it's the same equation. Body force, I'm saying net force F is equals to ma. What exactly is linear momentum conservation? Force is mass times acceleration, which is Newton's second law. Now we know how traction can be written, right? So I'm going to use the definition of Cauchy stress, which is this. T is nothing but sigma transpose times n. And then from here, from the second equation, which is relating to the integration over a surface, I'm getting the third expression rather, by using the Gauss divergence theorem. Okay, I've directly used the Gauss divergence theorem to convert the surface integral to a volume integral. Why did I do that? Because on two other sides I have volume integrals on the first expression. Okay, so it is, and Gauss divergence theorem allows this kind of converting a surface integral to a volume integral. Okay, so if it is possible to convert the other way, one can do it, but there is no further simplification unless you know what the distribution of body force or the displacement is. So we converted, please correct this, it should be capital S. So converted a surface integral to a volume integral using the Gauss divergence theorem, and I'm replacing it back in the original expression. Okay, now all of them are being integrated. All three integrals are on the same volume. All three are volume integrals, and the region of integration is on the same volume V. And I'm rearranging it and I end up getting this. Now, what was V? We said V was an object and V is any particular volume in that object. Okay, just that it is not discretized. So if I pick up any portion of this body, no matter what the numerical value of the volume V is, this expression should be valid. Okay, so we are saying essentially there's an integral. It should be 0 if I take any volumetric portions in the body. There's no specific, there are no specifics on the shape of the body or even the quantity of the volume. So this essentially means by zero value theorem that the value of the integrand should be 0. Essentially, this should be 0 at all times and for all volumes. Okay, so this is the expression that we get. Now this equation is called as force equilibrium equation or force balance equation or simply equilibrium equation. Different authors use different names. In other words, one can call it linear momentum equation as well, because that is what we started with, and we have gone it. We have included the elastic nature of the object. Assume that the body does not deform. Okay, if the body does not deform, which means there is no strain and there's no stress. So essentially, what you are having is F is equals to ma per unit volume. That's what we are saying here. And the new term which you have is the term which is taking care of the elastic nature of the object. Right. And so, as I said, this equation, people call it as force balance equation or equilibrium equation. One can as well call it as Newton's law in elasticity, Newton's second law. Right. And we are going to deal with static cases in this course. Okay. So I'm going to set the derivative with time as 0. So in case of static equilibrium, this is how the expression is. B plus del dot divergence of the stress is 0. You can write it in initial form or its component form. Now this is an expression which is very familiar to you when you have used in strength of materials or mechanics of solids, where you have analyzed an element and the components of the stress on it. Okay, so instead of writing these many expressions, this long, I mean, how many terms are there? 1, 2, 3, 4 into 3. Instead of 12 terms, we can write it in terms of 2 terms. So that is the advantage of, that was the primary use of resorting to the initial notation. All right. So now that we finished the linear momentum equation, let's see. Okay, then the last one, which is the angular momentum. We will revisit these conservation laws towards the end when we particularly use the conservation of energy principle. Okay, again, the same concept. For an object V, body V, I'm taking a particular volume, and this time I'm chosen a point P in the volume, and I am trying to balance all the moments due to these external forces as well as surface tractions as well as the body forces. I took a point P in the volume V. Okay, and I'm trying to say, okay, the net moment about at this point must be conserved. Okay, that's what, and these symbols have the same meaning as before. So I'm considering this point P. So I took a volume element which is at a particular distance from the point. And then I'm considering some point on the surface. Okay, and then I'm going to integrate all over the surface. I'm taking some volume. Okay, and I can integrate over this volume. So all I have is what is moment? Moment is R cross F. R is the position vector, F is the force vector. How do I write force in terms of body forces? It is B times dV, and R is the corresponding position vector. Likewise, I can extend it. TdS represents the corresponding dF. All right. So this is the net moment, and one can set this to the net angular momentum, rate of change of angular momentum. Right. So this is total. When I say momentum here, we are referring to. You may want to please correct it. We are referring to the angular momentum. All right, since we are dealing with static problem, one can as well set this right hand side to 0 or this expression to 0 on the whole. Now, if I have skipped the derivation here towards what we towards the final output, again you would use it is easier to solve this using indicial notation. Now that we all are familiar with indicial notation, I recommend that you solve this in indicial notation and try to simplify this expression. And if you do all the algebra, rather this cross product matrix, cross products in indicial notation, you would end up with this. You will end up by saying sigma is nothing but sigma transpose. And since you are working it with in indicial notation, we would end up with this particular expression saying sigma ij is sigma ji. So the stress becomes a symmetric tensor due to the conservation of angular momentum. Okay, so I have skipped the derivation because in the larger interest, we need to move towards solving problems. And since you are familiar with the indicial notations and vector algebra, I have skipped that details. The output is this: using conservation of angular momentum, the result is that in a classical solid, the stress becomes symmetric. It's a second order. Now stress is a second order symmetric tensor. Previously, until now, it was only a second order tensor. So it had 9 components. Now, because this is symmetric, because the stress is symmetric, you have sigma xx, sigma xy, sigma xz, sigma yy, sigma yz, and sigma zz. And these term again becomes sigma xy. This becomes sigma xz. This becomes sigma yz. So you now have 6 components of stress. Originally, when we defined stress using the Cauchy's notation, it was defined as T is traction is equals to sigma transpose n hat. Right, sorry, n hat. Yeah, that's it. So it is a stress was a function mapping a first order tensor to another first order tensor. And that's why stress became a second order tensor. Okay, stress was a function mapping a first order tensor, which is the unit normal to the surface, towards the traction, which is again a first order tensor or specifically a vector. So how does the Cauchy stress definition translate to? Now, originally it was sigma transpose, and now that sigma is symmetric, sigma transpose is nothing but sigma. So from now on, we can drop the transpose sign. How does the dynamic equilibrium change? This was the original expression. Now that stress is symmetric, it can be written this way. Okay, in a much simpler way. All right, so conservation of angular momentum makes the stress a second order symmetric quantity, and the Cauchy stress. So these are the only 2 other equations that where stress is involved. So wherever sigma transpose is there, you can replace it with sigma. So it does make these couple of changes. Now, in deriving this, you would assume that, while in going back to this particular slide, I've set this to 0. The question arises, what happens if this expression is not 0? If I am dealing with a dynamic problem. What is a dynamic problem? Say a wave propagation problem, wave propagation in a string. Okay, that's one easy example. That's dynamic wave, or a shock explosion onto a solid. These are all dynamic problems. So even there, the stress tensor remains a symmetric tensor. Why? I will only give an overview. One can as well do a very detailed formulation. We are not solving dynamic problems, but it makes it doesn't hurt to look at why the stress tensor remains symmetric even in case of dynamic problems, as in even when the right hand side is not 0. So the moment is the same as before, and angular momentum is this, and we know rate of change of angular momentum is nothing but the net moment. Again, Newton's law in for angular momentum, second law. So I'm using substituting these expressions, doing it should be V. All right. And if we look at the scale, okay, I'm doing a very simplified analysis. I'm not doing a detailed analysis. I'm just trying to show how this can be valid for a small element, which means it is valid for every other element. So volume scales as d cube. What is d? D is the characteristic dimension. So if this is the element, volume, if and I say d is the some characteristic, okay, since we are taking a cubical element, the volume in fact actually becomes d cube. But if one is ambitious and takes a not so simple shape, and if d is a characteristic size, the volume will shape as approximately d cube, and the surface area will shape as again, sorry, this is a typo. This should be capital S, not small s. The surface area shapes up as scales up as d square, and the position vector roughly scales as d. Now, essentially, this means the integrals. I have r, I have dv, which means I'm scale this integrand scales as d power 4. So is the second one, and the last one scales as d cube. Okay, since the element size is small, d is a very small quantity, which means these two terms are zero, are infinitesimally small, which means this term also has to be small. That's the simplification step that I'm trying to use. So it basically means if I divide everything by d cube, I have a small element d. This is d, and this is some entity which we are yet to figure out. And as limit d tends to 0, this term tends to 0, which means this term will have to tend to 0. And what is traction now? Traction is sigma times n. So we pick up a cubic element because that's whenever we define stress in Cartesian, we are working on a cubical element. And you expand traction in terms of stresses. So now if you have observed, the time component has vanished. By doing such an analysis, the time component has vanished, and if you expand, if you take any two opposite faces and try to evaluate, say, the moment about z, then you will again get the same set of results saying sigma 1 2 is sigma 2 1, or sigma xz is same as sigma zx. Okay, by doing this scaling analysis, that concept of time has been removed. Okay, and you will end up with this kind of expression, which if you split it with on a cubical element such as this, you will once again get the once again get the concept that the stress tensor remains symmetric even for dynamic problems. We will be solving one or two dynamic problems. That is why I thought it is essential that we understand that stress tensor remains symmetric. All right. What happens when a stress tensor is rotated, when the coordinate system is rotated? The concept which we have seen before as well. I thought for completeness, we can relook at this problem and solve it instead of the transformation matrix. We can try and look at it in a different way as well. So Cauchy stress definition is this: traction is sigma transpose times normal vector, and I can write this in matrix form. The transformation matrix is Q. We'll use the same notation, and I can correlate the tractions of the and normal vectors from the old coordinate system to the new coordinate system. So T prime is in the new coordinate system, so is N prime. So I have transformed the original components of traction and normal to the new coordinate system. And in the new coordinate system, again, our Cauchy stress tensor law should hold true, right? So now I'm going to substitute for T and N. All right, sorry, T prime and N prime using this vector transformation law. Right, and I'll express, so by substituting it, I'm trying to express everything in terms of the old coordinate system. Okay, so this is what I have. And so this is the last expression that we have. I'm just moving to the next page. So this is the expression I have. And the only T is known, N is known, Q is known because you know how much we know how much we are rotating the coordinate system by. So the only unknown remains sigma prime. So we'll simply do some manipulation. So I'm pre-multiplying everything. What is traction? Traction is nothing but stress times N. So, and then I'm rearranging the terms. I'm moving everything to one side, taking N common. And this should be valid for any normal vector. And therefore, this is the expression that we get. And since Q is an orthogonal matrix, remember Q is not a tensor. Okay, when you say a tensor, it is referring to a particular, it has components with respect to the dyad formed by a particular coordinate system. Q is a transformation matrix. It is relating one coordinate system to the another coordinate system. So let us not call it as a transformation tensor. It is, let us, Q is simply a transformation matrix. Since Q is orthogonal, you get the expression for sigma as this. All right. So this is the same old thing which we have seen previously. We solved when we looked at a second order tensor, change of components of a second order tensor under coordinate rotation. We did derive in a different way. Now this is one similar way, not entirely different, but the concept essentially remains the same. Likewise, you know what principal stresses are, but let us see if does anything change once the moment it becomes a symmetric tensor. So principal planes are the planes on which traction is perpendicular to the plane. What is the principal plane? When you have a second order tensor, we know already what an eigenvalue and an eigenvector is. So the eigenvector for a stress tensor refers to the corresponding principal plane on which the traction is perpendicular to it. All right. So whatever you learned through Mohr circle, you can as well relate it now. Whatever I said, just said, the unit normal vector corresponds to the principal plane, and this vector is nothing but that eigenvector which you get by solving the eigenvalue problem. And the corresponding eigenvalues are the principal stresses. Okay, so since our eigenvectors are all normal unit vectors, I can start with this. So I'm solving this particular problem. There is stress. We are looking for that plane in which when the particular traction is only scaled. Okay, the traction is only scaled. That's what we are trying to say. It is along the normal of the plane. So rearrange it, and for non-trivial solution, for non-zero value of unit vector, you would need to set the determinant to be 0. Right, and whatever polynomial expression we get through solving this determinant is called as a characteristic equation. I only skimmed through the mathematics because we have already seen how to calculate the eigenvalues and eigenvectors of a tensor. Okay, in particular, now it has even simplified further because sigma becomes a second order symmetric tensor. Okay, so the details of which have already been discussed in week 1 lectures. Right now, let's say I have this as 3 principal stresses. The goal is to now write the principal stresses in terms of whatever stress we have. Okay, without doing any coordinate transformation, or let's say you know the stresses, you know the principal stresses and you know the normals. How can we identify the stresses? Okay, there is principal stresses we know, sigma 1, sigma 2, sigma 3, and the normals are known. Even if you know 2, you should be able to identify the other one, and this particular procedure will tell us. Now, what exactly do we mean by this? Each of these sigmas and n must satisfy this, right? Sigma p. I'm going to call this as sigma p, and np is a vector. Right. So, which means I can as well write this in terms of matrices, right? Whether it is n1 or n2 or n3, I can write it as my matrix. Sigma p is a scalar, np. So I have 3 such things, 3 such equations, and I'm jointly placing them together with on the left hand side as well as the right hand side. I'm not doing anything different. I'm simply writing 3 of those equations, placing them side by side. I'm doing a horizontal catenation or concatenation, and n is 3 by 1. This is 3 by 1, and this is 3 by 1. right? And which means essentially this particular matrix becomes 3 by 3. And this is also 3 by 3. In fact, these two are identical matrices, right? And now this has also become 3 by 3. On the left hand side, there's a 3 by 3 matrix. On the right hand side also, there's a 3 by 3 times 3 by 3 matrix. So I'm going to call this particular matrix as N, some capital N, for convenience. There's nothing specific. So which means this long looking expression equation can be simplified to this form. Rearranging, you would have this. I'm writing the stress, given a stress component, given a stress tensor. Even if you know the principal stresses, we would be perhaps be in a position to identify the values of N. Or if you know the principal normals, without even solving the eigenvalue problem, one can identify the principal stresses, values of the principal stresses. So the analysis done on this particular slide is not something new to you. Is that I've recast whatever we know. We already know how to solve an eigenvalue problem. So I'm just trying to write the final outputs in terms of the original stress tensor. Just so that in the case when we know our normals, or when we know our principal stresses, or when we know two sets, we should be able to identify the third one without actually going through the long process of taking a determinant, then solving the system of equations. Okay. Right, so we would stop at this particular point, and in the next class, we will look at what constitutive relations are. All right, so the previous lecture was on traction and stress, and right now we have looked at what conservation laws are. And this is the last new concept that we will learn, and from there on, we will combine all these concepts towards formulating and solving problems in elasticity. Thank you.